My name is Vlad. I'm a student at West University of Timișoara and a software developer at Press Labs in the infrastructure team. At Press Labs, we are doing WordPress hosting dedicated to publishers. We have a custom infrastructures that can serve millions of page views per hour, and an awesome support team that will take care of your WordPress site. Now, in the last 4 years, we had some achievements. We had 45 million page views during 24 hours on a single site, 6 million page views with an hour on a single site, 2.2 billion page views in our busiest month, and 0.00006% outreach in the past 12 months. That including the maintenance on some sites. But as you can imagine, this business is far from perfect. In our relationship with the clients, we discover a big conflict, and I'm sure that you also discover it, is the conflict between the non-technical part and the technical part in a project that involves some code. In our case, the problem was that our clients and their development team, they both share the same SFTP credentials, and basically, without any versioning control system, the both parts wanted to change this website in the same time, and usually they ended up broking the site. And they start blaming us, they start blaming each other, and shortly, a lot of chaos emerged. But what if I tell you that we found a nice solution, elegant, beautiful solution, just like a unicorn? But unlike a unicorn, this solution is real, and it's called GitFs. Now, GitFs is a fused file system self-versioning based on Git. Basically, what it does, it takes all this nasty, complicated, ugly Git object structure and transform it in some more readable structure. We have here two main directories, a current directory and a history directory. In the current, we have the current snapshot of the repository, and in history, we have a group of collections of the snapshot at each commit, grouped by day, and after that by hours. For example, on April 6th, we had two commits, one at 2051 and one at 2052. The first one containing only the README file, and the second one containing the README and the PyCon Py file. Well, as you can see, it's very easy and simple to understand for everybody. Now, if you don't believe me, let's get to a demo. I'm having here, I'm trying to simulate the remote part and the local part. So we'll have here a bare Git repository. Here we have the developer's work, and I'm going to mount my file system in MMT directory. Who here is familiar with Git objects? Cool. For those who don't know what a Git object is or look like, well, Git is going to store all the information related to the commits of the files in a .git directory. And it looked like this. Now, if I want to see what files were committed at one commit, or what was the state of the repository at a certain commit, all I need to do is take the commit, and after that, just do some plumbing commands, and I can see that in this object actually is a tree object that has a parent and so on and so forth. The tree object has two files, two blobs. Actually, they have two blobs object, and if I want to see the content of this blob object, I can do that and just showing up the content. Now, let's go back to the business. In order to mount my repository, I have to deliver the remote URL. In my case, is the local Git repository, then the mount point, and just some options. like the cloning path, some timeouts, and that's it. As you can see here, my file system is mounted in this mount point, and we have two directories. In current, we have the current state with 2 files, and in history, we have only one folder with a bunch of commits that happen at 1 a.m. in the morning. Now, if I want to change a site, let's say that I want to add a new file. The other way, like that. Now, in the background, my file system is gonna do some magic. It's gonna push to the remote. And if I'm going to pull on my developer branch, I'm gonna see that he created a new commit, update file 3. I have 3 files with 42, and it's working either way. I can say that I want 43 to be in file 3. I'm going to add that. Gonna push to the master, and if I'm going here in the current, yeah, it's 42. And I'm still waiting. Maybe it's gonna change to 43. Yeah, a little bug. Sorry for that. It happens. Last night it was working. Okay, now you can see it's as 1 to 3, and it's all written in Python, and it's free and open source for everybody. Now I'm going to tell you how was it made and how can you build a similar file system. First of all, because neither of us in the company didn't know how to build a file system, well, we needed to do a little bit of research, and we needed to find 2 main components. The first component was something to deal with the Git objects and all the Git magic and all the versioning and stuff like that. And the other component needed to deal with the file systems. Now, for Git, we didn't want to use the actual Git command line tool because well, we needed to manage all the processes. It was a big dependencies for us, and we want something very light with a low memory footprint. So we choose PyGit2, which is a library on top of libgit2, which is a library written in C that can manipulate very low level those Git objects. I'm going to show you how you can clone a repository and push to a remote branch. First of all, you need to set up your credentials. I'm using SSH here as the transport layer. You need to pass a user, the public key, the private key, and the key phrase. After that, just clone the repository, search through all the remotes and find the one you want to push, and finally just push to that branch. It's easy. In 6 lines, I can clone the repository and push to a remote branch. Now, for the file system, I want something to be able to build that file system as fast as possible and as painless as possible. So we choose FusePy, which is a wrapper on for libfuse, and here I'm going to show you how simple it is to do an in-memory file system. All you need to do is to create a class that inherits from operations class from FusePy, and after that just implement all the syscall that you want to implement. You just dump this code in a memory.py. If you have FusePy installed, just python memory.py, and you have in-memory file system which does nothing, but it's pretty straightforward and pretty easy to write. Okay, now the first iteration was dirty. And when I say dirty, I mean very dirty, because for each syscall, we needed to check in which directory we were. If we were in the history or in the root directory, we can't rename the history, or we cannot rewrite the history. So we need to raise the certain error. If we are in the current directory, we can do the actual logic. But this code is really buggy and really bad. So in the second iteration, we tried to fix that. And what we did was to create some views for each directory. For current directory, created current view. For history directory, the history and commit view. And for root directory, the index view. And between those views and the actual syscall, we put up a router. The router and the views are both implementing the operation class from FusePy. And when the syscall emerge, that syscall is going to be passed to a router. And the router is going to instantiate the proper view and execute the read method. For example, if you want to read a file from 7 months ago, you just go to the history, do a read syscall on that file, and that syscall is going to be passed to the router, and the router is going to instantiate a new commit view and execute the read method. Now, our logic, our view diagram is pretty basic. We have a view, a main view class that is inherited from operation and login mixing from Fuse. That class is inherited by pass-through view and read-only view, which of course are inherited by current, index, history, and commit view. Okay, for the upstream synchronization, like when you're going to, if you're going to write and create a commit, you need to push it to a remote, to a remote server. And we did that with just git push pull using the PyGit2 API. But shortly, we found out that a lot of conflicts can emerge because you don't have a clean staging area. And in order to solve those conflicts, we implemented always accept mine strategy. But in PyGit2, you don't have that kind of strategy, and you need to implement it by hand. Let's simulate a simple conflict. Let's say that we have a master branch on a remote server and on the local server. Both local and remote branch have 1, 2, and 3 as a common commits, and on the remote server, a developer pushed the commit 4, 5, and 6, and on local, our file system created the commits 7 and 8. Now, in order to merge with always accept mine or always accept the local changes, basically we need to move the commits 7 and 8 after commit 6. How we can do that? First, we need to find out that 3 is our less common commit, split those branches in 2 branches in merging remote and merging local, and after that, just cherry pick those commits 7 and 8 and renaming the merging remote branch in the local branch. You can implement another strategy. You can, for example, you can implement a strategy in which if there are some conflicts, you can create 2 forks of those files that are in conflict. Now, for the third iteration, we wanted to see if we had any problems in the real world, because now we had a file system, you can push commits on the upstream, you can create commits, you can solve conflicts. It's pretty stable and it's a pretty good working file system. So we choose a really big repository with 70,000 commits, and to do just a simple listing on the history a directory, it took like 34 minutes, which is quite bad, and it's quite a performance issue. And in order to fix that, as you can imagine, we can implement some caching layers. Actually, we have 3 caching systems. First of all, the first and the biggest one was to just read all the Git objects when you're mounting and store all the Git objects in the memory, because what we did was for each operation, for each read or whatever, for each syscall, we always read those Git objects from the disk, load in memory, and so on and so forth. Now, if we only read those Git objects once and invalidate this cache on each new commit, we're gonna get a nice performance boost. The second one, we saw that our router it's initializing a lot of views. Well, for each syscall, he's gonna create a new view and execute just maybe the same method, and is wasting a lot of memory. So what we did was just cache all the views in the memory, but we shortly saw that a lot of memory is wasted, and when you're mounting the WordPress repository and you cache all the views, you're like 2 GB of RAM exceeded, so it's not fun. So we implemented an RDU cache and cache only the important views. And finally, we implemented a cache for the gitignore submodule files, because each time when you want to write something to a file, the current view needs to go and open that gitignore file and check all the paths and see if, okay, can I write to that file, so on and so forth. And what we did is just read the gitignore file once, parse it, and invalidate that cache on each new commit. Now, for the upstream synchronization mechanism was pretty okay. I mean, just pull, create new commit, push, pull, create new commit, push. But when you want to unzip a big archive, let's say that you want to write at once 1,000 files, you don't want to have 1,000 commits. You just want to have one commit. And to implement this strategy, we use 4 Mon components. Use the fuse threads. We have the fuse threads. We don't have any control on those because the fuse is gonna create whatever, how many threads he wants. After that, just a commit queue that is gonna do the communication between fuse threads and the sync worker. We have a sync worker, which is just a Python thread, and a fetch worker, which is a Python thread, and basically he's just gonna fetch a certain period of time. Fetch from the remote. The fetch worker has another option called the idle, and if, for example, you don't have any activity on the file system for more than, let's say, a day, he's gonna go in idle mode and he's gonna fetch less often. I say that he's gonna fetch at 2 days. Because when you're mounting 2,000 repositories, or let's say 200 repository on a server, and all of them fetch at the same time, you're gonna have some networking problem. Now, let's say that we have 4 files open in write mode, and 3 of them just finish up the writes. When the fuse threads will close those files, 3 commit jobs will gonna be passed to the commit queue. The sync worker will gonna proceed it those commit jobs, and he will wait a certain timeout for new commit jobs. If nothing is happened, he's gonna create a commit. Now, in the meantime, the fetch worker is still fetching changes from the remote. Now, if the sync worker has nothing else to do, like he didn't receive any commit jobs, he's gonna create a new commit. As soon as he created that commit, he will want to push that commit to the upstream. But first, in order to do that, we need to merge, and in order to merge, we need to have a clean staging area. But we still have one more file open in write mode, who is doing writes on the disk. And in order to block those writes, we have the sync worker, and using a Python event object, he's gonna say to the fuse threads, okay, now I want to sync, please don't open any more files in write mode. He's going to wait for all the writes to finish. Let's say the fourth file finish up writing. He's gonna wait and see that there is no more activity. He will create another commit. After that, we'll say to the fetch worker, okay, I understand that you have changes, please don't do any more fetching, because now I'm trying to merge and push. After that, he's gonna merge, push to the remote, and just resume fetching and resume the writes. Now, as you can see, it's quite a nice experience, and quite a nice learning experience about concurrency. For the final remarks, we have an Ubuntu 12.04 and 40.04 package. Somebody from the community did a package for Fedora and Arch Linux, and we also have support for Mac. The final takeaways, even if somebody will tell you that Python is slow, Python is not good for concurrency, Python is not good for do complicated stuff, you can actually build a production-ready file system in Python. And as you saw earlier, it's very easy to build a fuse file system, but it's quite tricky to get it right. And a soft one, by combining the right technologies, you can give a lot of power to the non-technical people, because we are all developers, and what we want to do is just help other people to do their job easily. Do you have any questions?
Hi there.
Hi.
I was wondering, does this GitFs, could it possibly support branching? Could you have, like, for instance, a branch system in the file, in the way the files are sorted, and if so, how would that work in the structure?
Yeah, for now you can do with just one branch. You can follow just one branch, but if you want, you can go with open source. You can fork it, and I imagine that you can have here like branches folder, for example, a master folder, or I don't know, your branch, and yeah, you can do that.
Cool, thanks.
Yeah, you were mentioning in the beginning that like people were overwriting files and getting angry at each other using SFTP or so. I still haven't figured out, like, how do the person that wants to edit the style sheet that doesn't know anything about Git, how do they run this on their Windows machine or whatever? Like, how do they actually use GitFs on the client side, all the different people?
Okay, for now in our production, we have the SFTP server, and on top of that, we have mounted this file system. And basically, when they don't know how to use Git, or you cannot use this on Windows, but they receive the SFTP credentials, and you're just gonna open the current file folder and write the changes. Their development team, they know Git, and they are using the Git the right way, but our clients, they are non-technical people, they just know SFTP because SFTP was used like 5 years ago and they're still using.
Okay, so it's like SFTP for your clients and Git for your, okay. It's not like within the same company that like because the two different people using SFTP, they will still overwrite each other's file and be.
Yeah, well, our clients have a development team.
Yeah.
And basically, the development teams know how to use Git and stuff like that, but they don't know, and it's very hard for our clients to learn Git. So basically, you have to put them together to use the same tool. And the same tool was, the common tool was SFTP for both of them. Yeah.
Okay, so even though you overwrite files, maybe you now at least can see the history that you did so. Like.
Yeah, and now you know who overwrites what.
Yeah.
Yeah. One over here.
Yeah.
One thing I was thinking, just looking at objects, have you thought about or explored or looked at the possibility of the Git objects being stored in S3 or Swift or some kind of object store that's online?
Yeah, we didn't think about that, but yeah, it's a quite nice idea. Do you have something more specific in mind? Like
no, it's something I've thought about before and haven't done, but it looked like you came close. And I've used Git Python before. I haven't used PyGit 2. I don't know if that's better, but just kind of, since you were exploring sending the objects out, I was wondering if you had thought about that, or if you were actually sending the objects over, but you're not. It sounds like you're just doing a push, right?
Yeah.
Okay.
Do we have any more questions? No? Thank you very much, Vlad.
Thank you.